Welcome to the Analyzing Android Malware webinar, From Triage to Reverse Engineering. My name is Vitor Ventura. I'm a security researcher with Cisco Talos. I love mobile malware. I really hate insecure instant messaging. And of course, I do some reverse engineering and I do APT hunting. I'm located in Portugal, and this is our agenda for today. We'll start with a brief introduction to the Android applications. Then we go through triage. Afterwards, we have then our triage. Now we can do the unpacking, the obfuscation, and environment checks bypassing. Of course, we should take a look at patching some code. It is useful in some cases. And finally, we'll look into how to find command and control routines, and we'll have a wrap-up. So first of all, let's think about the objectives. When we are doing malware analysis, what we want to do is first, we want to classify the malware to its type and family so that you know what is it doing and what's the risk that presents to us. We want to identify and or confirm the features that it has. We want to collect IOCs, and we want also to identify the command and control routines, being that the beaconing or the command parsing and the data exfiltration, how is it done? Of course, throughout this webinar, you will see lots of things that can be automated with some tools, but the idea here is to show you how to do them for yourselves in case of something fails. So, an Android application is basically a zip file containing a lot of information. There's a lot of XML files that will contain strings, the manifest, the accessibility features, all of that. But keep in mind that these XML files, they're in binary format. So just unzipping the APK and trying to read these files won't work. These files need to be unpacked and decoded. For that, we usually use the APK tool. It's a pretty common tool and it works really fine. The code of the application will be in the classes.dex file. There may be more than one file of this kind. But if you load the whole APK into the decompiler, some of them will pick that up and show you the source tree in a flat structure, so you won't see that there are more than one dex file. However, if you are using things like APK tool or backsmall, you should be aware of this. This file will also contain some configurations. That can be configurations for things like the Google Firebase cloud messaging service. Or you will also find the same configuration in the manifest file, which contains a lot of information. So the native libraries that may be there, but that doesn't necessarily mean that they are being used. But they can be there if needed. So a manifest, it's pretty much an XML file with a lot of nodes with a lot of information. When we look at the manifest, what we want to see is things like the permissions, which shows you what the application can do, the priority of the receivers, which, for instance, in this case, you can see that the telephony here on line 56, for this kind of action, this manifest in particular has a priority of 999. So this means that this malware will receive the SMS before any other application. And that means that it can also delete it so that the user never sees it. I also mentioned the accessibility. Here it's also defined the accessibility. However, this is just the action. In the manifest, you don't really know what can the application do with the accessibility framework. But then again, you have that configuration on an XML file that you can read once it's decoded. So now let's talk a little bit about the tools. For the tools, I will use JetX mainly. It's one of the best decompilers for Android out there. It will decompile 90% of your samples. Then you have Bytecode Viewer, which is really good because it's almost like a front end for different decompilers. So you have their JetX also, but you also find their ProCyan, Fernflower. JD GUI. So all of those different decompilers. And what is helpful is that if one fails, you can see the code on the other. Or you can even see two different decompilers side by side and decide which one is better for you. And finally, I like Smalley to Java. I recently came across this because I had this sample where the routine for the C2 wouldn't decompile on JetX and wouldn't decompile on any of the decompilers that came with bytecode viewer. So I wasn't stuck in a place where I couldn't see the code. However, all of these were able to get the code in Smalley. Not in Java, but in Smalley. So this tool is really cool because you can pick up the Smalley code and transform it into Java. And the reason why this works is because it doesn't try to analyze the opcodes. It just picks up the Smalley and transforms it into Java. So in this case, it worked perfectly. So on other tools, we have APK tools that I've told you about. Smalley and Backsmalley, it's useful because if you have a payload, which is just a DEX file, you won't be able to decode it with APK tool because it's not an APK, it's just a DEX. So Smalley and Backsmalley are the tools that are used for that. And actually, APK tool uses that. Then if you do patching, you'll need zip-aligned APK signer and key tool to generate the key, to align the zip, and finally to sign the zip so that you can install it on the Android. And we have also free instrumentation toolkit, which I have in this webinar. 90% of my usage, 99% of the usage I do, it's with the emulator, the standard emulator that comes with Android Studio. There's a lot of others out there that you are free to use. In some cases, I've also used a physical phone, but 99% of the cases, this is just enough. There are a few switches that I want to call your attention to. So the first one is this one, TCP dump. This will capture all network activity. Of course, you will like to use your burp so that you can intercept the calls to the backend. I understand that's perfectly fine. However, keep in mind that there are some malwares that actually do socket calls, so raw socket calls, and that won't go through the HTTP proxy. So it's nice to have at least a capture just in case you have to compare some stuff. The other thing, which is also really nice, is to have logcat always stored in an output. Sometimes the screen rolls over, you lose some information. Having it like this allows you to go back and check it without even thinking about having to store it. So for free, it's more or less the same thing. There are a couple of switches that I want to highlight to you. So the first one is log-o, so log all output of Frida into a log file. Same reason as the emulator. And the other one is the no pause. The no pause switch is really useful because in some cases when the malware is trying to unpack the payload, if it stops, if the malware starts stopped, it will crash. So having the no pause is really important for you to just keep going. So let's start with the triage. One of the first things that you want to do when we're doing triage is look at the manifest. It will have a lot of information for you. It will give you a broad idea of what the malware is doing. The permissions, you can immediately understand which kind of resources it tries to access. The services will give you a hint of what's going on when the application is down. So basically, things like taking care of accessibility, trying to keep screenshots, all of that will be on a service. The receivers are also important to capture, for instance, SMS as they arrive. So all of these are good indications of what the malware does. There's one point which is also important, which is the main label. The main label will be run on the first time the malware is executed. And that is where all the persistency, everything is set up. So this is one that is good to look at least once. And then, for instance, you should look for the on boot completed message, which allow you to understand the persistency mechanism. So let me show you now a video of a triage. We'll start by unpacking the application using APK tool, as I told you. As you can see, there's the decoding of the XML Android manifest, which is important, and then the back smalling of the classes. So let's just see if there are any native library calls. We go to assets, and we just do a find on the shared object. Notice that JSON? That's interesting. Okay, we have a lot of shared objects, but each of them has a different name and it's for a different architecture. So this kind of tells me that they're not used at all. But we will see. Now let's take a look at the manifest. So here we can take a look at the permissions, of course. As I told you, this is a real gold mine of information. There's a lot of permissions here. The record audio usually points towards a rat. The SMS, well, that serves both rat and banking Trojans. Read contacts also. There's a lot of banking Trojans that will spread through the contacts. We will also take a moment to take a look at the package name, because that is what we will need in order to start the application when we are instrumenting it with Frida. In this case, it's traps with hotel. Not really difficult to memorize. Now let's see what else we have on this manifest. Let's look for the main activity. So here we have our main activity. We know that from the Java point of view, the package is actually called promote critic denial. Nothing to do with the package from the application point of view. Keep that in mind. So our main class is WFG. This is the one that we will check because this is the one that runs when the user clicks on it. So it may only be needed at the first time, but we'll need to check it. Then we have the broadcast. So this one has a broadcast SMS with a high priority. This means that this class will receive any SMS before anything else on the device, allowing it to pretty much delete the SMS so that the user never sees the SMS. Well, then we have this class actually does a lot of stuff, including the persistency. If you notice the boot completed, that's what we'll call, that's the action that happens when the device actually finishes boot. So let me just pause this a little bit. So this class will be the one that takes care of it. This class is a really important class. And just before we go to the accessibility, one more detail. If you notice, this class also looks for the package added and package removed. So it will be able to keep an inventory of what's being added. So, for instance, if you think of a banking Trojan, if the bank application it's not installed, it's not doing anything, but it can be just that doesn't mean that the malware will be stopped. It will just be waiting, and when the victim installs the banking application, it will detect that. So it may be able to do something about it. Now, for the accessibility, we know that we have accessibility services here. They are defined. However, on the manifest, usually you don't know exactly what the malware can do with the accessibility framework. What you need to do is actually look for that file, the XML-UZK, because that is the file that will actually have everything that the application, or in this case the malware, can do with the accessibility framework. And we know that the class that will take care of these events is that one. So let's take a look at that XML file and see what's inside. So resources, XML, and now we have the UZK file. Let's take a look at that one. Right, so let me just fix this a little bit so that you can see it a little bit better. Okay, that's it. So the malware will capture all events on window content change and on window state change. This pretty much means that the malware will actually be able to interact with any application that the victim is working with. And then, as you can see below, it can retrieve window content. So this means that, for instance, if the user is reading a Signal message, a WhatsApp message whatever kind of secure messaging service the victim has, it will be able to retrieve the content. Whenever the Windows pops up, the malware will receive an event and it will take care of it. And for instance, it can retrieve the content. So you can pretty much build a whole rat with the accessibility framework and a few more things. And this is a good example of it. Now let's take a look at the other XML file that we have here. Okay, so this is the file that defines the policies for the device byte. So this is where it's defined. So this is where we are defining the policies for the device admin. Basically, this means that the malware will be able to lock the device and will wipe the data. This can be used, for instance, to do a ransomware. So there are a lot of things. Even if a rat, for instance, would be interested in having this because it would be able to wipe all the data, deleting himself and further making it more difficult to do any kind of forensics. So now let's see if the malware is packed. You notice that we have the package, which is called, the package from the Java point of view, which is called promote critic denial. So if the malware is packed, we will not see this on the small code because we have just unpacked and it won't be there. If the malware is not packed, then we will have the classes there and we don't need to search for them anywhere else. So let's see, promote critic denial. Do we have it here? So let's see, find promote. We don't. So this pretty much tells us that the malware is actually packed. So what have we learned on this triage stage? It's permissions. Based on it, it seems more or less like a rat. It also has capabilities to do ransomware by locking and wiping the device. It's packed, definitely. There's no doubt. The native libraries doesn't really seem to do anything. Three different architectures, 3 different libraries. So at first glance, they don't really mean anything. And from the accessibility point of view, it will be able to exfiltrate any kind of messaging and secure messaging that is around. So this seems more like a rat. But now we need to unpack the code. It's packed. We need to look at those classes and know exactly what they do. First, let me explain a little bit how most of the packers work on Android. So pretty much what they do is that they will hook the onCreate method that exists on the application. And they will, at this point, do the unpacking and write or somehow load the classes that are actually defined on the manifest. This happens because the first thing that is created on an Android application is the application class. And that's responsible for doing all the boot up and calling the activities which are on the main, which are defined on the manifest. So by doing this overload, they can pretty much start the execution before any of the activities from the application itself. So let's see a video on how we can do some unpacking. So first of all, we will run the malware instrumented by Frida with all the options that I told you before, and with a little script, which I call triage, but pretty much records the file activity from the malware. So one thing that we want to do while we are running the malware for the first time is pretty much give it all the possibilities that it wants. So if it wants to have a lot of permissions, let's give it all the permissions that it wants, even if it doesn't request it at the beginning. Keep in mind that some of the malware will try to request the permission as it goes, but we want to give it everything right at the beginning so that we can see what it does while we are recording it. So we will try to do it now. Well, it seems like the malware crashes, but okay, not a problem. We'll run it again and go and give it the permissions manually. Okay, eventually it would request them while it was actually running, but since we don't have the means to emulate all the command and control activity, we'll just give it all the permissions and see how it behaves, and we'll record it and then we go back. During this analysis, I will reinstall the malware several times. So whenever you see restart command, that's pretty much is deleting the malware from the device and reinstalling it so that I can have a fresh start. So now I've killed the emulator, and I'm going to take a look at the file that I've got. One thing I know for sure, I will have a lot of repeating lines because I've seen them going through the terminal. As you can see, there's a lot of this ring0.xml. It's clearly where it stores some kind of shared premises. So I don't really want to know this right now, so I will do just a unique filters. This way I don't need to deal with all the repeated lines. So now let's take a look at the unique ones. So we know that our file is packed, right? We know that the malware is packed, and at this point we don't have the source code, the code or the DEX. So we want to retrieve that. See that XML that has .cur.prof? That's usually created when you have a DEX. So that's the profiling of the application. So that JSON may not be a JSON. And remember that we saw that when we looked for the native libraries. It was there. I noticed it, but I didn't comment on it. So we also have the ring0 here still. There's those CPU info is also interesting. Sometimes it's used to detect if it's running on an emulator or not. So that might be interesting to check later. A lot of founds. This is not really that interesting. So yeah, lots of founds, definitely lots of founds. So let's just move along. We want to check if that JSON is really a JSON. It's in the package, so maybe we are lucky and it's not even obfuscated. Okay, we are not lucky, as you can see. So now let's go and run our emulator again. But now we know that JSON is our code. But maybe on the device itself, it's not obfuscated anymore because it needs to run. And to run, it cannot be obfuscated. So if we are lucky, it will be on the device, not in the package, and it will not be obfuscated. So let's go there. So it was on app dynamic optex. Let's see. Maybe we are lucky. Okay, this is a DEX file, so it's not obfuscated. We are in luck. So now we just need to copy this over and load it into JEDEX and see if it's actually our payload. If it's our payload, it will have the same classes and the same package that are defined on the manifest. If it's not our payload, it can be anything else. We need to double check. So let's extract the file from the emulator into our file system. Okay, let's do that. It is with the adb pull command. Now that we have it, let's do backsmally on it. So here is a good point where you cannot use APK tool. You have to use backsmally. Okay, so we have a promote. I remember that one. So let's double check out promote critic denial. So let's check if we have that class. One of the things with code, sometimes you just pick the wrong window. Let me just fix this. Here we go. So promote critic denial. Let's see if we have that on the code that we have just decompiled from that JSON, which was not a JSON, by the way, it was a DEX file. Okay, we have promote, we have critic, we have denial. Let's see if we have that weird name in Smalley. Yes, we have. So this pretty much proves that this code is the code that is on the manifest. So this is our payload. So this is pretty good. So we need to rename it in order to load to JEDEX. For some reason, JEDEX will need the extensions to be defined as the proper ones. You cannot open a JSON file; it won't work. So now that we have renamed it, let's load this into JEDEX and see the code. Here we go. Let me just push this into the window. So It's a little hard to see. Let me fix that also. So you can see. Okay, so now you can see it better. So promote, critic, denial, glove, and we have a lot of classes here. This is the one that we were talking about. Yes, and we don't have a problem decompiling this one. This is the Java code for that class. So this is a broadcast receiver. And yeah, definitely. This is our code, so there's no doubt here. So now we have seen how to unpack this code. So first of all, what's on the triage script? The triage script is a really simple script that will pretty much log all open files. And this is really important because this allows me to see a lot of things. So for instance, it helped me identify the payload. If there was any kind of emulator checks based on file, it will detect that, just like the one that I mentioned to you, the CPU info. It's one of those methods. If it was checking, if it was rooted, it will probably check if there was the su command. This will also detect that. The usage of preferences file, which kind of preferences files, as you saw the ring 0, there was a lot of that. If the malware was actually using the native libraries, you would see them being open here. The fact that they were not open here, or probably that they are not being used at all. So this allows you to see a lot of things for the beginning of the execution. And as you can see on the comments there, this also allows you to actually bypass some of these checks, because if it's checking if the file exists, you can actually manipulate this script so that it's trying to hide the file that it's trying to check. So in this case, we didn't need to focus on trying to find the algorithm that's obfuscating the code. We didn't focus on that. We just want to find either the jar file or the DEX file that is being loaded, and we'll work it from there. Focusing on the encryption and all the obfuscation mechanism usually will take you through a rabbit hole. So this is a really, really way simpler way of doing stuff. Now, what if the payload was not on the device? What if it was not there? How could we approach this? So let's see video number 2. Okay, so in this case, it's a different sample, so let me install the sample first. So it's installed. As you can see, there's a lot of permissions there. I've granted all the permissions. It's ready and executed. So let's see if we have anything there. I know this sample is packed, of course. I'm just going to show you if we have any kind of DEX file there in the same path. So we have the same package there. There's the application. Let's check the app files, for instance. There's nothing there. Let's see if there is something on the optimizations. So here we have the profiling also. So we know that our file will have that name and it's a .jar. That already helps. That's a really hint, but we don't have the file. So let's run this application with our triage script. Let me just pause this for a bit. As you can see here, there's nothing going on while this screen is on. So as you can see, the Frida is not dumping anything. This is what I talked to you about the no pause. This malware, if it was paused, it would create problems because this screen is being showed before any of its activities are launched. So we need to keep going now. And once we hit that button, you can see that everything is now starting to happen. So now it's when it's trying to unpack and all of that. So as you can see here, we have our payload there. There isn't much activity yet, so this is fairly simple to take a look. But one thing we know for sure, we have our payload there, or what it seems to be our payload. So let's just close the emulator and take a look at this log. Okay, so here we go. I have a lot of what's needed, and we have our file here. So the file existed at some point in time, right? We know that it was there because it was open, but for some reason, it's not there anymore. So the reason may be because it's being deleted. So if it's being deleted, what we need to do is actually prevent it from being deleted. And in order to do that, we need to hook the application using Frida so that when it tries to delete the file, we won't let him. So let's take a look at that script. We take care of the file. I use code. I'm used to use VI, but in this case, I'm using code so that it can be easily seen. So I've already prepared this for the previous one. So let me just replace this path and replace this condition. And I will pause this afterwards so that I can show you what's going on. So pretty much what I'm doing is that I'm hooking the unlink, which is the function that is responsible for deleting the files in libc. And I'm saying that if it tries to call unlink, delete something else. It's important to let the function be executed, and it's important to return the OK to the malware, because if it has some kind of error check, it may not run. So in this case, we want to let it think that the file was deleted. Another important thing here is that you should always do an alloc, because otherwise what may happen is that if you have a path here bigger than the one that it tries, you will have an overflow in the variable. So if you do an alloc and you just change the pointer, you are safe on that. So let's now run the malware again, but hooked with this script. As I told you, I've reinstalled it several times over these videos, so I'm just install it again. And we'll see. It's also important to leave a little log message so that you know that your hook actually ran at the right place, so that you can control what's happening. You'll see the importance of this in the next video. So let's run the package. Actually, need to fix this, not a J, it's an F, and the no pause. Okay, so everything is running. See, we have a message there. Did not delete our payload. Seems like it worked. So the best way to check that is to go inside the emulator and check if the file is there. If the file is there, then we are good. If it's not there, something went wrong. Let's do that then. Maybe we are lucky. Well, not lucky. Maybe it worked. Here we go. We have our file there. It worked. So now what we need to do is take it out again and load it into JADAX and compare this with the manifest and see if it matches, then we are good. We have our payload. We can start doing the reversing of that payload. If something is wrong, we need to double check and see if we did something wrong. So it's there. Let's open the file. Actually, I already have it open here just to show you. Let's check one of the classes. The SMS received one seems like a good one. Let's check this one out. So FBTINK. Let's open that one. And now it's G. Okay, we have it here. And yes, definitely this broadcast receiver same class, it really feels like a class that would handle SMS. So we have been able to unpack it. So the malware actually deletes the payload after unpacking it. So we were able to identify it and we prevented from deleting it. So now we are in a position where we can actually look at our payload. Let's finish this video. It's done. Let's go back to the slides. So now before we wrap up this section, what if during that pause that you saw, the malware was actually checking if it was running on an emulator or not? What would we do then? And you guessed, I have another video to show you. So one thing that is important to always keep in mind when we are doing this kind of analysis on Android is that not all versions of the operating system will have the same behavior. So as I told you before, if the application is packed, it will need to create a class which extends the application class, which is the one that will actually do the unpacking. So I've opened a couple of classes. I just wanted to show you this example. So let me just go through this. Before I go on, this is the class that actually checks for the emulator. I just prepared this in advance in the interest of time. So you'll see here a lot of things that immediately point you to some checks. You'll see the generics, all the generic strings that I've showed you before. We have here all the different kinds of emulators that you can find, usually the Genymotion, the Nox. So all of these are pretty much checks to see if it's running on the emulator. Now, going back to this class, we don't know where it's being called yet. It can be called in a variety of different places. So let's try to find out which one. So one thing that we know, let's just go back 2 millimeters so that I can show you. So one thing that you already can see is that this class A is being called from within the package itself. So there's a big chance that it's actually this one. So let's see what happened here. So here we have a class, it's running A, and one thing that is important immediately that you can catch your eye on is that it only does something. So this is the class that is called at the beginning of the previous one, the one that is extending the application, and it's only executing something. There's a lot of stuff that is only executed if this doesn't happen. So this actually gives you a hint that this might be the check. The other thing is that if this doesn't happen, so if this code never executes, because this is the one that does return, it throws a low memory exception, which doesn't really make much sense because there's almost no checks for memory here, and usually this is done by the framework, not the application itself. So let's check this class in particular. Okay, so if I turn off the obfuscation from JetX and actually go back there, we will notice that I've already renamed this just to make sure that we would understand it. It would be easier for us to check. So going back to the original names, this is the class, okay? This is the class that actually runs the emulated checks. Now, it's important that you have the name of this class, because if you want to hook it, you need to hook it by the real name, not from the obfuscated name. But let's take a look. Of course, I've already showed you this class, so let's just try and hook this. So we'll write a little piece of code, of course, Java perform, and what we'll do is that for that specific class, we will hook it and return false, so that it would run. Remember that that's the negative. So I've already seen it. Let me just show you how to create the script that will hook it. So first we need to define the class. That's it. And afterwards we need to actually hook the method. So class interceptor. Now we need to check which method it is. And if we look closely, it calls check emu, and that pretty much redefines it and defines the class, instantiates the object, and then calls the method. If we go to the implementation, you can see that there's a C there, so it's renamed from C. So the method that we want to hook is C, and we want to overload it. Keep in mind that we should always pass all the parameters, but in this case there are no parameters, and that's why we are not defining anything, and I can show you that right away. As you can see, there are no parameters for checkemu, so that's what we are defining. Let's just fix this with an N that is missing there. Another implementation of this is simply returning false. That's what we want to do. We log it just to make sure that we actually executed our hook, and then we just return false so that there's no emulator there. Keep going as you were. Okay, let me just, yeah, that's it, and it's done. So we'll now execute it as usually, and then we'll see the log to see what's going on. Notice that I'm running a older version of Android just to show you. So in this case, it's crashing. Why is it crashing? It's saying that it did not find the class. So different versions of Android will give you different results, as different versions of Freedom may or may not work. You need to test it out. What happens in this case is that we are trying to hook a class that at boot of the application doesn't exist yet. Remember that this class will only be instantiated after the application starts. And in this case, it's actually not being able to hook it because the class doesn't exist yet. This is a problem. We won't be able to hook it as we want it. So let's try the exact same scripts, exact same thing, but performed on a different version of the operating system. So in this case, it's running. We were actually able to hook it, but there's something weird here because we have a message. So it didn't delete the payload, which is good. But if you notice, we have a method to hook, which is running. It's being hooked, but it didn't actually work because you can see that the checking for the emulator presence were never logged. So something did not work as we wanted. Let's do a restart. Let's take a look again. Let's load our triage script and see it again to see what we are missing here. So that's done. Let's run it again. And what do we have here? Now let's see. We have our hook there. And yeah, we have the hook there. There are some checks. Those checks are usually checks for the emulator. So we see that the checks for the emulator are happening before the hook. And that may be a reason why we're not seeing it. But we also see an open file of uudd. So what we can do is actually move our code for the hook to be executed when the uu.dd file is open. So we do a mix. I've already done it here so that you can see. What I've done is that actually I'm moving the code of the hook from the generic place to be executed when the file is open. And as you can see on the log, let me just finish commenting this out. So as you can see on the log, the uudd file is open before the drivers and the CPU info. So if I can place the hook there, I will probably be able to hook it in time so that it won't check for the emulator. See, I have a if the open file is that, uu.dd, then that's when I do the hook. And that forces the hook to be done before the check of the drivers. So I've told you that a lot of Android stuff is asynchronous, and that's true. But in this early stage of the application boot, that is pretty much sequential. And seems like it worked. As you can see here, now we have checking for emulator presence, replying false. So what we did was we move the hooking above. And you don't even see the calls to open, the proc info. All of that was erased because we did the hook. So let's go back to our presentation. So we can do the instrumenting of the unlink to prevent the class from being deleted. The other thing is there may be cases where the payload is actually in memory. If that happens, then what you need to do is to hook the in-memory DEX class loader and just save the DEX buffer into a file, and you have your payload anyway. The other thing that I want you to remember is that the timing on the hooking is important, but it can be controlled. You can look on what's going on above or below and trying to do the hook in a way that will happen when you need it to happen. Now let's talk about string deobfuscation. Let's see our video that I got ready for you. And so first of all, in this case, we know that the strings are obfuscated, right? But let's search the main class and look at what's there. It's clear that they are obfuscated, and we have clear signs that it's base 64 encoded. So one of the first things that we want to do is to check where are they being decoded. So we can just follow this method and see where it takes us. So here we have our obfuscation method. One thing is that it's local, and if it's local, that means that, let me just pause the video. Since this is a local method, this means that probably each method will have its own obfuscation method. So, and that really doesn't help us a lot. But now looking at this, we can see that the base 64, there's a base 64 decode there, but then there are a lot of functions. Let's keep the movie going. So we have a new object class H that is called, let's see what this does. Yeah, notice that we have the same string going in. Now let's see what the H does. And this is a package level class, as you can see. So this is not specific to the main class. So that does give us some help. Eventually we can do something that will work for all the classes. It seems like this is some kind of key generator that is then used to deobfuscate the string. So I've already made the script that will help us to do this. So first I need to log what's going inside. So I'm logging the base 64 string, just like that. And I don't really care about what's going out of the decode. I just want to log the what's going in so that I can then associate what's in with what is out. So as you can see, and then I have my H. So I'm hooking the class H and the method B. Let me just show what the method B does. So the B is called by the A method. As you can see here, let me just pause the video. So as you can see on where I have the cursor, so H is created, has a method with a few bytes, which seems like a key, and then method A is called out of the object H. And that's the method A is the one that is going to take care of what's going out from base 64. So what we want to do is to hook the base 64 to see what's going in, and then we want to actually hook the method A or B, because A calls B, in order to see what's going out. And that's what's going inside the constructor of string to actually construct the string. So let me show you. Here we go. So we have, as you can see, A always calls B. So we really can hook either A or B. It's the same thing. I'm just hooking B. And then we also must be careful. And this is where I will actually log what's going out. So because what's coming out of there are just char codes, I'm transforming that into a string so that we can see what's going on. So we also could try to hook directly the constructor of string. However, my experience is that often doesn't really work. So I opted always to do a specific for each case. So let me just pause the video again to show you. So here we have, first we have the base 64, which was what's going into the base 64. Then we have what's going out as the bytes of the shortcodes. And then we have actually what we want. This way, by doing it like this, I can correlate the base 64 with what's going out. And that's what we want to do. At the same time, I also have all the stack, the call stack, so that I know each string where it's being used. And this really helps to then correlate the classes that are being called, where it's being called for, and what's being used for. So let's go back to the slides now. So just as a recap, hooking the constructor of string, it can be overkill because you'll have a lot of information. There's a lot of internal calls of the framework that will actually use the toString or the constructor. So it will be overkill. You have a lot of information. Also, it really depends, as I've showed you before, different levels of the operating system will have different behaviors. And most of the times, this really won't work as you wish. So hooking the methods of the obfuscation themselves is usually a little better, and also gives you more understanding of what the malware does. Another possibility, of course, is that you could look at the obfuscation algorithm and write it yourself. The disadvantage there is that because it seems like it has a key, you'll need to know each key for each method, and not all keys will work on all methods. So that may require a lot of time, a lot more than what you need if you do it like this. So just as a summary, you need to hook it, then you need to capture the output so that you are sure that you can link that with what you want. You print it to the console and then just return the output to the malware. That from there you can understand exactly. It's important that when you hook it, you actually return the output to the malware if it needs to run. Another thing that you need to keep in mind is that some versions of malware, some malwares that will use native libraries to do the string obfuscation. However, it's exactly the same method that you need to apply. There's always a call from the Java side into the native libraries and something that comes out. And of course, you can do it right at that point, or if you wish, you can directly hook the native code as we have done with the unlink, for instance. Okay, now it's time to talk about patching. It's rather simple patching. So first of all, we need to understand exactly what you want to patch. In this case, for instance, we are changing these conditions. So this malware is checking if we don't have a Google SDK or in any of the properties. Basically, it's checking if it's an emulator or not. So in this case, what we're going to do is change those conditions so that it will bypass this kind of checks. So we need to unpack the code, of course, see it in Smalley. You have a syntax highlighter for Smalley for Visual Studio Code. And also, if you want to do unpacking, use APK tool with the option -R, because that won't touch the resources. And I have come across some samples that if you try to decode the resources, then the repacking will be a problem. So once you have identified the code that you want to do, what you need to do is basically change the Smalley. And in this case, you change the condition if not easy. You just change it to if equal to z. And that's it. That's simple. You change the code right there. So afterwards, what you need to do is to repack everything. As you can see now, I've done it, and the code now changed. The condition is changed. And this is enough to bypass. You might ask if the malware doesn't do a self-check. I have not come across any of the malware that would do a self-check on the code. So I think that for now, this is also a solid option if you want to work with it. What you need to do afterwards is that you need to sign. So you need to generate any kind of certificate, doesn't really matter which kind of it is. And you can just, after that, you align your zip file with the command that you can see there, and finally you sign the package. And with that, you can then install it on an emulator, and you won't have any kind of problems. It's as simple as that. Let's find the command and control routines. Let me load the video again. So basically, we'll start. We have already decoded our strings, so let's try to do the easiest thing, which is basically look through our decoded strings and see if we find any kind of URL. And if we do, okay, we have a URL. Now let's try and search for that on our code. If we have it, maybe we'll get lucky. Remember that this is the sample that we extracted the payload from. So as you can see, there's nothing there. And of course, there's nothing there. The reason for that is the URL is never in clear text, so we need to search for the base 64. That's why we need to keep the base 64 linked to the output. Okay, here we go. We have a variable. Let me just pause this. So we have a variable that seems to be decoding our string and assigning it to something else. So this is probably not the class that we're looking for, but let's keep tracing. But now what we can do is that we can see where this variable is used. So let's just rename it so that we know what it is. And now let's see where it's being used. So we have it being used on the attribution, which makes sense. And then on our main code, remember that our main class was called WFG. So it seems like it's being used exactly on the main class on onCreate method, which makes complete sense. So we are on a good track. Okay, now we can see, so one thing that you need to look at this is that we can see that it's being called for a lot of times in this method. So let's check what this method does. Okay, this is a shared preference method. So it seems like the malware is trying to keep the URL in a shared preference variable. Since you have a commit here, we know that this is an edit. So let's just rename this method to shared prefs put so that we know that it's a put. And since we are here, let's take a look at the one below. And the one is doing a get string, which means it's doing a get. So let's rename it also. And now let's go back. As you can see now, it makes much more sense, the code that we're seeing. It's being our C2 URL is put on a variable. Let's rename that variable also so that we can know exactly what we're looking for. So chances are that we won't see any more references to our original variable, but we will see a lot of references to the variable inside the shared preferences that hold the value. So now we'll check where is this being used. And here we have a lot of options. So let me just pause the video a little bit. You can see here that it's being used as a put. We don't want a put. What we want is a get, because we know where it's being stored. Now we want to see where it's being fetched so that it can be used. Let's take a look. Okay, so all of these are put. We have a get here. You see this get? So let's take a look at that code. This is storing our URL into a variable j. Another good hint here also is that, as you can see, there's a connect URL and a concat of the value of our URL. And then there's a method being called. Chances are that this method is actually a logger. So if you go and take a look at your logcat that you have stored, you will probably get the information there. That's also a good tip. If you don't have the information on the obfuscated strings, take a look at logcat. Chances are it will have a lot of information useful there. So our call is being called here. Our URL is being called here. So let's take a look. Okay, one good information. It's using OK HTTP client. So we are definitely on the right track, and this is actually the method that does all the beaconing to the C2. So this is what we were looking for, and we just found it. Another good point here is also that we can see where the response is being held. So I will show it afterwards, but if we want to check the protocol, chances are that if we trace this variable, we will end up seeing all the commands and all the features for this malware. But I will show you that a little ahead. A good point also is also to rename the method so that we know what's being done. And this allows us to track all the beaconing. Now, one thing that I will also show you right after this video is that what if is there something else? So this one really shows you how it's being done at the first time. We can search for it and it shows you clearly where it's being used. However, let's imagine that we have something else. Let's search again for other methods. So let me load the other video and see this one. Well, let's take a look. So we are at the same point at the beginning, but now what we want to do is begin our search. Let's imagine that we don't have anything to go from. So one thing that we should do is to search for the URL. The video is a little fuzzy, but what I searched here was URL, as simple as that. Keep in mind that a lot of the Android code is made with strings. So if you search for things like URL, chances are that you'll get something. So as you can see, there's a lot being used on URL. Also keep in mind that a lot of this may be part of the framework itself. So you don't want to follow all of them. You want to keep your searches within the package that you know. Avoid going into the framework as much as you can. So there's a good one here. So we open this one, and this one is interesting because it's on a sync task. As I told you earlier, a lot of things that happen inside Android, they are async calls. And this means that you might never get to see a direct call to the method that actually holds the code that you want. So to keep that in mind. Being an async call, it won't be called directly. What you need to think is, if there is a point where it's being called, it's being done through the API, or not the API, of course, through the framework itself. Okay, so as you can see here, there is a method called doInBackground. So whenever an async task is executed, it will call the doInBackground. The same way it will call the onPostExecute if there's something to do when it finishes the execution of the async call. So what happened is you have this method, but this method is only called from the doInBackground. But if you try to check where the doInBackground is called, it's not ever called. There's never a call in your code for this. And the reason for that is because this is an async call, and when the async call is created and executed, the framework of Android itself will call always this method. So keep that in mind. And now we have here a new connection. So let's trace this back and see what kind of connection this is. Because it may be a secondary C2. So we need to trace this back. So let's see where this method is used. Okay, we have this function that is just used there. So now we know that the base 64 encoding for this URL. So now we can go back to our strings that we decoded and see if we have it there. And here we go, we have it. Okay, now we know that it's not configured at all. It's just the beginning. But this really helped us to see the full flow. So in this case, this malware seems to have two kinds of C2s. There's one that is configured and another one that is not configured. So on one, on the previous video, we started by seeing that we have a hint and we follow that hint to the code. In this one, we just go blindly searching for things like URL. We could have searched for HTTPS or other kind of strings. That would help us to actually do the search. Let's see if we can find out where it's being used. Tracing the method doesn't really take us very far because it goes directly to the doInBackground. So let's trace the async call and its creation. So now we see that there is one method that is doing all of this. So let's just open this method and see what is it doing. So it's basically creating the async task and executing it. So just like we saw. So this is what will trigger the doInBackground method. so there is no direct call to our C2 contact method. Okay, now we have seen this. Let's just do a recap. So to search for the C2 routines, you can look for traffic in the PCAPs, look for URLs, look for domains, IPs, all of that. You can do it on the PCAPs, but you can also do it in the logs that you collected from the freed execution or from the logcat that you have collected. So all of these hints will help you to search. Then you can look at the code. You can look for the format for URL, for socket, for the URL connection, and then you need to follow the breadcrumbs. But all of these will be there. So it's not often that you will see obfuscators that will hide everything on there. Also be aware of annotations. There are some cases where the code is annotated, so the path for the C2 or the IP or the host for the C2 is on annotations, and that may trick your decompiler into missing it. So be aware of that. And finally, there are also malware that will use SMS or push messaging services as C2. Again, keep that in mind. Take a look at the SMS routine. You know that you can check it directly from the manifest, what class is handling the SMS routine. So keep in mind that. Now about intercepting the communication itself, I won't go through all the details of setting up a burp or installing a certificate. Just keep in mind that if the certificate pinning is implemented, you can also bypass that. There are several methods. You can patch. If you can find the certificate, you can change the certificate, or you can instrument the application so that whenever the app is checking the certificate, you will answer correctly. There are plenty of free scripts online to do that kind of manipulation. Now let's try to find the features. We have seen where our C2 is handling the code, and as I told you, what we need to do actually is to trace back the code that you have found and see where the answers are parsed. So let me show you another video. Just closing the old one up. Let's now see the second video, and here we go. So remember that we saw the contact C2. We saw its usage. You have seen where it's being worked. So now what we want to see is actually the function that does the call. And what we want to do is tracing that function so that we can know how it's handling the answer. So let's try that. Okay, so we have here, and we have an if contains. That's an important thing. So showing that there is a if contains usually is a way to parse a C2, especially on Android. So now that we are in a point where the code where we can see if there is a cycle of a switch statement, a cycle, all of that usually points towards some kind of protocol parsing. And there's a lot of ifs here. Oh, and here we go. Here we have a switch statement here. And seems like all the features have useful names. You can, of course, find some malware that instead of having these clear names for the commands, it will find just some kind of codes in integers or some lettering code that it's not as obvious as this one. There is one thing that is interesting on this one. As you can see, there's a C. So it's assigning if it's equal to what they are looking for, it will assign just the variable with a number. It's not doing any code, and especially is not doing any execution. So, okay, we have a second switch that will actually match the numbers, and with that, it's actually deciding what to do. And here we have some code. It's interesting that they are using HTTP URL for something like this, but okay. Well, I'm not going through all the details of what this malware does. The point here is to show you how you can actually find the code for the C2, the protocol. Okay, now let me go back. So from the malware features point of view, once you find out the code that is actually beaconing the C2, you can find out how it's parsing the answers, and you need to take it from there. Just follow the breadcrumbs again. A lot of Android stuff, and because you can almost every time get Java code, is actually following the breadcrumbs and go to the places that you want. Again, keep in mind that there may be native code involved, and you might actually have to reverse C language or something like that. But anyway, in those cases, the procedure is exactly the same. And now for the wrap up. So there's a lot of information here. I'm not going to read all the bullet points here. I just want you to remember that most of the things on Android, it's asynchronous. So there may be a lot of async calls that you may be missing. So keep that in mind. Not everything is linear. That's especially true when we think about the push messages and all that kind of stuff. It's not just limited to Java. I think that you maybe have .NET. There are other kind of languages involved in this. There are languages that have a lot of boilerplate code that you need to navigate through before you get to actual code that you want. The process of extracting the payload is relatively simple. Don't get lost in trying to reverse the actual algorithm of rebuilding it. Just pick it up when it's already rebuilt and ready to use. Now, as for other stuff, Manifest is actually a really gold mine. Keep that in mind. Take your time reading through the manifest, understand which classes are used, when. A good example of asynchronicity is, for instance, an activity can run independently of everything else, and it may just be waiting for an SMS to arrive. One thing you can do with the emulator is to simulate that. Send an SMS to your device and see what pops up. For instance, in this case, when I was running the string deobfuscated, I got 0 strings regarding the SMS handling because I didn't send an SMS, and that code never ran. But if I had sent an SMS, that would happen. So keep in mind that all of that asynchronicity. Good thing also to keep in mind are broadcast receivers and accessibility, especially accessibility. Accessibility gives the malware the capability of pretty much reading anything that goes into the screen. That goes to private messaging, passwords, SMSs. Everything can be read through the accessibility. You can actually almost build an entire rat just out of the accessibility. Okay, so keep that in mind when you're reviewing your malware. Just some final thoughts. Use case-sensitive file system. There are a lot of obfuscators that will use the exact same name for the class, but it will use uppercase and lowercase in the name of the classes. And what happens is, if you pick up a deobfuscator that will unpack all of that, they will end up overwriting the classes because they have the same name if the file system is case insensitive. So keep that in mind. Native calls, as I have already said, it's not a headache. They always need to be called from Java, and they always need to be read from Java. So you can hook them easily, either directly when they are called or in the native code itself. There is a point where you need to be careful. I have seen some anti-instrumentation kits that will try to prevent your FRIDA from attaching because they will use native calls to do better control over the process. In those cases, what you need to do is to hook them before they are called. Keep in mind that you can hook, and the order, you can control it in the proper timing. So with that, you can actually bypass this kind of systems. During the webinar, one of the questions was that if there were any other kinds of packing. And of course there are. And I mentioned that we had analyzed a malware that actually was receiving the payload through the Google Fire messaging service. So this is that malware, and let me show you how you can detect that. So let's open the malware. Here we go. So if you look at the manifest, we will see that there is a class. In this case, we have a main, so we are going to look at the main. Just before we continue, you can immediately see here that there is Firebase configuration and play services. So this could be a good indicator that there is some usage from the malware to the Firebase, but we don't know what it is at this point. So let's continue. So we'll go and see the main application. There isn't much interesting. Let's take a look at the onCreate method, which is the first that it's going to be executed. As you can see, most of it is just preparing what the user will see. But there's a method here that is called, which we don't know what it does. So let's take a look at that one. Okay, looking at the declaration, we immediately see that this has to do with Firebase. So this, of course, raises questions. Let's take a look at it and try to understand what's going on. Of course, this being from the payload, then there's a little more, from the framework, there's a little more that we need to look. Before we go there, I just stopped the video. I want also to take a look at these two calls. Handler post delayed, two of them. Keep in mind that on Android, the best way to schedule an execution for a while, it's not to put a sleep on it, it's to actually define a handler for a post-delayed action. And this is what's happening here. So let's take a look at this. So basically, it's just showing something on the screen. And this is also showing something on the screen, but this one is interesting because it's actually showing something to the user, which is saying that the application does not support uninstallation in progress. Let's see if it's really doing the uninstallation. Actually, it doesn't seem like it, right? It's actually creating an action that it will be executed, an intent. So, and then it's calling another post delayed that we can take a look at, which will show that the application is uninstalled. So basically, this is tricking the user into thinking that the application is uninstalled. This is actually a really good method so that when the user clicks on the application, it will say that it's not for that operating system, it will say that it's uninstalled, and it will remove the icon from the user desktop. So the user will think that, well, this application just didn't work and it's not there anymore, which is a really good way to trick the user into thinking that nothing really bad happened. Okay, so this is where everything is happening, and this makes complete sense. So let me just, so it's sending let's just go back on the video a little bit so that I can show you. So what this method is doing, let's go from here. Let's see what's happening while it's supposed to be uninstalling the application. So this method, what is actually doing, and you can see this from the log, often the log cat will have a lot of useful information. So taking a look at the log cat is really important. In this case, what's happening is that it seems like they are sending the FCM token to the server. So the way that the Google Fire messaging service works is that when an application is started, a token will be generated. And that token needs to be sent to the C2 so that the C2 can actually contact Google services and send a push message. So even on this case, it always needs, there's always the need to first maybe unique contact with the C2. After that token is delivered to the C2, well, they don't need to contact the C2 anymore because the malware can receive all instructions from the Google messaging service. So it seems like what's happening here is that they are sending the token to the C2, or at least retrieving the token at this point. Now let's just take a look what that other method does. Let me understand what's going on here. Okay, so we can see that it's actually gathering location data. this can be really useful for the malware operators to decide if they actually deliver or not the payload, depending on who got infected. Let's take a look at these two methods. So this is the method. It seems like it's also getting some information out of the accounts. And let's take a look at this final one, see what's happening here. While post, yeah, this might be the one that is actually contacting the C2. Yep, here we go. So yeah, so it's building the information to send to the C2, which is that one, and we just need to find, and here we have the C2 in clear text. So this is all run at the first point of the execution. This is just, as I told you, the first execution that needs to happen. It's setting everything up, and afterwards, it doesn't need to do anything else. Of course, it wouldn't need to do it exactly on the first run. It could do it later, but in this case, it's doing on the first run. So by the time it contacts the C2 and actually sends the payload, it won't need to do anything else from the C2. It can retrieve all the information from the Google messaging service. We have here, this is actually from one of the malware that we were looking through the webinar. And as you can see here, this method wasn't deobfuscated at all. It wasn't decompiled at all. We don't see what's happening here. But however, we do have all the smally, but it's really hard to understand what's going on here. So what we do is that we just copy this into a text file. I won't show you, but this method actually wasn't decompiled with the bytecode viewer either. And we save it as a text file, as I was saying, just copy over all the data. Let's just give it a name. You can call it smaller just to make it easier. So we can see that it's being parsed by code viewer, but what we really want to do is convert it to Java. So now I'm going to use the smally to Java tool. It won't be as good as JEDEX, but it will be Java, which is way better than what you see when you are looking at smally. It gives a great help to understand the code. Just run it. And now we can go inside the smally directory and find, here we have file, and you will see that it's Java. And you also have all the smally entries that gave you the Java, so it does really help you to understand. Of course, then you can remove all this with a couple of regex and just have the pure Java. As you can see, it's not perfect as the one that you can see on JEDEX, but it really helps you to understand what's going on.